In this course, you will learn about models of battery cells and how to use them. And in this lesson, you will start to learn how to build a model of a lithium-ion battery cell. Models, remember, are sets of equations that describe something, and usually we use models to describe something physical. So in our case, we're building models or sets of equations that describe the behavior of lithium-ion battery cells. In order to do this, we will notice that the way that a battery cell responds to an input stimulus can be approximated very closely by the way an electrical circuit responds to an input stimulus. So that is, the way that a battery cell voltage responds to a change in electrical current will be modeled by how a circuit's voltage also would change to the same change in its input current. And the model that we develop using these ideas is called an equivalent circuit model, because the circuit behaves in an equivalent way to how the battery cell behaves. And equivalent circuit models have some desirable properties. They help give us a feeling for how a cell will respond to different usage scenarios. And second, these models will form the basis for the battery management system algorithms that you will learn about in the remaining courses in this specialization. In this course, you will learn about battery cell models by starting with a very simple model, and then we will progress step by step to refine portions of that model to describe better and better how an actual battery cell works. So we begin by looking at the simplest possible model of a battery cell, and that is by comparing the battery operation to that of an ideal voltage source. In this model, the cell voltage is modeled as what we call an independent voltage source. Cell voltage is considered to be constant and equal to the cell's open circuit voltage, or OCV. When we describe a battery cell in this way, we are saying that the voltage of the battery cell is not a function of input current. We're saying that the voltage is not a function of how the cell has been used in either the immediate or distant past. What we're saying is that the cell voltage is constant no matter what. Now, that's not terribly realistic. It's a very simplistic model or description of how a battery cell works, and this model is not very useful for our battery management system applications. But it does provide us a starting point, and with this starting point we can incrementally build better and better models of how an actual battery cell works. For example, we know that batteries do supply a voltage to a load, and it turns out when the cell is not connected to a load and is in complete equilibrium after all of its internal processes have come to rest, the voltage turns out to be fairly predictable. And this condition is known as an open circuit condition because the battery is not connected to a circuit. The switch is open, if you will, between the battery and the circuit. And you will see that when the battery cell is in an open circuit condition, it has what we call an open circuit voltage, and we will find that some kind of ideal voltage source will indeed be part of our final equivalent circuit model. But let's start to improve this model. And in order to improve this overly simplified battery cell model, we begin by recognizing that when a battery cell is fully charged, its open circuit voltage is different from when the battery cell is fully discharged. In fact, the voltage is higher when it's charged than when the cell is discharged. So we should be able to improve the model by including a description of the dependence of the cell's open circuit or rest voltage on some kind of an indicator of how much charge is in the battery cell. So to formalize what we mean by a cell's internal charge status, we define a quantity called state of charge, or SOC. When we talk about SOC in an equation, we will use the symbol Z of t if you're an American, or Z of t if you're from other parts of the world. One calibration point for our model is that it must agree with our intuitive concept that Z of t is equal to 100% when the cell is fully charged, and the other calibration point is that Z of t is equal to 0% when the cell is fully discharged. So we will define state of charge. But another quantity that's related to state of charge that we have to think about at the same time is how much charge is it possible for the cell to hold across the state of charge range, this interval between 0% and 100%. And we define this quantity to be the total capacity, or sometimes you see it called the total charge capacity of the battery cell. And we denote its value by the variable letter Q. Total capacity is usually measured either in ampere hours or milliampere hours. We begin to describe the dynamics of state of charge. In other words, how does state of charge change over time as a response to the input current to the battery cell, using a simple ordinary differential equation. In the notation that we use, if you see a dot on top of a variable, that means that we are taking the time derivative of that particular variable. So, in the first line of the equation, you see the symbol z with a dot over it, and I'll call that z dot, and this indicates or denotes the time derivative of z, or the time derivative of state of charge. We write that z dot is equal to -1 multiplying cell current, all divided by the total capacity of this cell. Notice that we have adopted a sign convention or assumption for input current. So when the sign of input current is positive, that means we are discharging the cell and the state of charge is going down. If the sign of cell current is negative, then we are charging this cell and state of charge is increasing. And that's exactly what we would expect. Also notice that in this equation, the input current is normalized by dividing by the capacity of this cell, so that when a total amount of charge has passed through the cell that's equal to Q, then Z changes by an increment of 1. And that's what we expect. If we start with an empty cell and we pass enough charge to equal Q in the charge direction, then state of charge should go to +1, or 100%. If we start with a full cell and we pass that much charge in the discharge direction, then we expect state of charge to go to 0, or 0%. Now we can take this differential equation and write it in a different way by taking the integral of both sides. And in the second equation, we see that state of charge at any point in time is equal to the state of charge at some initial point in time that we'll call t0. And then we subtract from that the integral of current going through the cell over the time interval between t0 and now, which we'll call t, all divided by the capacity of this cell. And these two equations are equivalent, and in some cases we'll find the first equation to be more useful to our purposes, and other times we'll find the second one to be more useful, but they say the same thing. Now we've slightly modified the circuit diagram from the previous slide to the one that's shown on this slide. In the previous slide you saw that the circuit had a constant independent voltage source that did not depend on anything whatsoever. It was just always the same voltage. On this slide, we've changed the circle that indicates an independent voltage source into this diamond shape that indicates a dependent voltage source. And if you look at it, it says open circuit voltage as a function of state of charge. And so here, the open circuit voltage is a function of state of charge, and it gives us the possibility of modeling different voltage levels at different states of charge. And so we'll look more at this dependence in upcoming slides. Now, I've presented the state of charge equation as an ordinary difference equation and as an integral equation, and both of these are what we would consider continuous time representations of state of charge. In our battery management system, almost all of our algorithms are going to operate in discrete time or in sampled time. So we need a way to convert the differential equation form into what we call a difference form or a discrete time form. And we'll look more at how to do this in general later on in this week, but for now I'm simply showing you the result of the conversion factor. So in this equation that you see, it says that the next state of charge at time index k plus 1 is equal to the present state of charge at time index k, which we're thinking about as being right now, minus the input current right now divided by capacity right now, and also multiplied by the sampling interval delta t, which is the time between any two samples that we are taking of voltage and current and so far in our battery management system. So we've gone from a very, very simple model, too simple, to one that's a little bit better, and we're going to refine it even a little bit more. Our next attempt at improving the model is to recognize that battery cells are not perfectly efficient. It turns out that not all of the charge that I put into the battery cell when I'm trying to charge it is actually used to raise the level of state of charge. Some of the charge can be consumed by side reactions, different chemical reactions from the one that's desired, and in doing so this charge is not used to change the state of charge, and so we could say that some charge is lost. Of course, it's not really lost, charge is conserved, but for the purpose of bringing up the state of charge of the battery cell in a useful way, we have lost that charge. To reflect this fact that the charging process is not perfectly efficient, we introduce a new quantity that is represented by the Greek letter eta, which looks a little bit like a script N in the Latin alphabet, but it's the Greek letter eta. And this is called the Coulombic efficiency of a battery cell. We assume or we model eta being exactly equal to 1 if the battery is perfectly efficient in the ideal scenario. But in reality, it has a value less than 1 when we're charging the battery cell, slightly less than 1. Usually it's in the order of 0.99 or somewhere around there. And so you can see that I've modified the state of charge equation a little bit by introducing this charge efficiency or Coulombic efficiency factor. Also, we write this efficiency factor as a function of time to recognize that it's not always the same. We are going to assume that the Coulombic efficiency is less than or equal to 1 on charge. If it's equal to 1, it's a perfect efficiency. If it's less than 1, it's a more realistic efficiency of a battery cell. Some of the charge is lost to these unwanted side reactions that I mentioned. Now, notice that the battery cell doesn't know, it doesn't have intelligence, so it has no idea whether the cell is being placed in a battery cell charger, or if just over time, somehow randomly, charging current is going into it. So when I say that the efficiency is less than or equal to 1 on charge, what I mean is that the efficiency is less than or equal to 1 at any instant in time that the battery cell current is negative. It's not only when I plug the charger into the wall to intentionally bring the charge up to maybe 100%. It's any point in time when charge current is flowing into this cell, this value of efficiency is less than 1. On the other hand, when we're considering discharge, we usually model the efficiency as exactly equal to 1. For some technical reasons, it may be possible for the cell not to be perfectly efficient on discharge, but it's sufficient in our models to capture the overall inefficiency on charge only for the purposes that we have in a battery management system. And that vastly simplifies the process for determining the value of this Coulombic efficiency value. I also want to point out that Coulombic efficiency is not the same thing as energy efficiency. So there's different types of efficiency that we can talk about related to battery cells, and it's important to understand the context and importance of each. So coulombic efficiency is equal to the amount of charge that we can withdraw from a battery cell divided by the amount of charge that we put into the battery cell. And this parameter, as I mentioned, is usually in the neighborhood of around 99% in high-quality commercial lithium-ion battery cells. Energy efficiency, on the other hand, is the amount of energy that we can take out of a battery cell divided by the amount of energy that we put into the battery cell when we charged it. And these are different things. Energy efficiency is often closer to 95% for a practical lithium-ion battery cell. You will see later this week, as we continue to refine the models of the lithium-ion battery cell, that these models will include a resistance term. And the energy efficiency is not perfect in a lithium-ion battery cell because some energy is lost through the resistance of the cell and dissipated as heat. And so this is a completely different mechanism for energy loss than it is for charge loss, if you will. So that's why energy efficiency and coulombic efficiency are really fundamentally different things. In the model that you've learned about so far in this lesson, you've seen that open circuit voltage can be a function of state of charge. This open circuit voltage versus state of charge relationship depends on the specific subchemistries that are used in the negative and positive electrodes of a lithium-ion cell. So each cell design from different manufacturers and from different types of cell that a manufacturer might sell to you will have somewhat different open circuit voltage relationships. And the figure on this slide shows the open circuit voltage plotted as a function of state of charge for 6 different battery cells that we have evaluated and modeled in our laboratory here at the University of Colorado, Colorado Springs. And you see that the voltage curves are all slightly different from each other. The 2 lowest curves are perhaps the most similar, and those are from 2 different types of lithium iron phosphate, or LFP, battery cells from different manufacturers, as it turns out. The 4 upper curves are for cells having positive electrodes that are some combination of lithium cobalt oxide or nickel manganese cobalt oxide or even nickel cobalt aluminum oxide, some of the chemistries that you learned about in the first course in this specialization. This illustration shows that the open circuit voltage for these different cells at room temperature, which we consider to be 25 degrees Celsius, but in fact open circuit voltage is a function of temperature as well as a function of state of charge. And so we can slightly modify the models that you've learned about in this lesson by including this temperature dependence simply by writing at this point open circuit voltage to be an explicit function of Z of t and also T of t, state of charge and temperature, as functions of time. Also recognize that sometimes in the literature you will see authors referring to open circuit voltage as a function of depth of discharge, or DOD, rather than a function of state of charge. Sometimes you will see them refer to open circuit voltage as a function of depth of discharge in ampere hours as well. And in that case, depth of discharge is equal to 1 minus state of charge, all multiplied by the total capacity of the cell. So those are 2 ways that you see it. But since there's essentially a 1-to-1 relationship between state of charge and depth of discharge, that we can write these 2 equations, it's possible and common to see open circuit voltage curves plotted versus depth of discharge as well as plotted versus state of charge, and recognize that all we're doing is we're switching the horizontal axis when we're doing that. So to summarize this lesson, you have learned different things. You have learned that the model that we can use to describe a lithium-ion battery cell in a very simple way has 2 equations. One equation describes how state of charge changes over time in a response to a cell input current, and the other equation describes how the cell voltage can be computed as a function of state of charge. You've learned that these equations can be written either in a continuous time differential or integral equation form or in a discrete time difference equation form. Often, we are going to find it to be simpler to derive the equation first in a continuous time description and then convert it to a discrete time set of equations later on. And ultimately, the battery management algorithms that you will learn about and use will use the discrete time form. So here I show you both as a reference to look back to later on. In these equations, you've learned that the total capacity Q is the amount of charge that the battery cell is capable of holding between state of charge 0% up to 100%. You've learned that the Coulombic efficiency factor eta is always between 0 and 1 and is usually very close to 1 for a practical lithium-ion battery cell. And furthermore, that this Coulombic efficiency is different from energy efficiency. You've learned that the open circuit voltage is the at-rest or equilibrium voltage of a battery cell, and that you will have different open circuit voltage values at different states of charge, and furthermore that the exact value that you get will depend on the chemistries used in the negative and positive electrodes of the battery cell that you are working with. And that brings us to the end of this lesson. In the next lesson, we will continue to develop this model further by adding features that describe more detailed aspects of how a battery cell responds to input current stimulus.